So, what's special about the orthogonal system 1 cos x, sin x, cos 2x, sin 2x, etc.? We have seen in the very first module that we are trying to write a general function f as an infinite superposition of these functions. And then we proved that when the original function is Holder continuous, then this infinite superposition actually converges pointwise to the original function. And we also looked at the Fayer's theorem and we looked at the L2 theory. So, now what is so special about this 1 cos x, sin x, cos 2x, sin 2x, etc.? Could we not look at other systems of orthogonal functions? For example, instead of looking at L2 from minus pi to pi, let us look at L2 from minus 1 to 1. In the sequence of Legendre polynomials, P0x, P1x, P2x, etc., also forms a complete orthonormal system. Let us look at L2 of the real line. That's also a very nice Hilbert space. So, for example, when you look at problems in quantum mechanics on the infinite real line, you will encounter this Hilbert space and you will have to work with this Hilbert space and you will have to work with orthonormal systems in this Hilbert space, and a classic orthonormal system on L2 of R is a family of Hermite functions that play a very important role in the quantum mechanical harmonic oscillator. We already encountered the Hermite's differential equation before. We shall encounter this later when we study this particular orthogonal systems of Hermite functions. So, now before taking up these two examples of Legendre polynomials and Hermite functions, let us look at the need for such a generalized orthogonal systems. So, this leads us to the topic of Sturm-Liouville problems and partial differential equations and generalized Fourier expansions. So, the title of this module is Generalized Fourier expansions or Sturm-Liouville problems and its applications to partial differential equations. So, let us begin with a simple example, namely a boundary value problem arising in physics, which will give rise to a PDE. So, what is a partial differential equation? Let us consider a circular membrane clamped along its rim, like the membrane of a tabla, for example, and it is set into vibration. The mean position can be thought of as the membrane being in the xy plane. The membrane can be thought of as a set of all points x squared plus y squared less than or equal to 1. For example, you can think of the membrane to be a circular membrane of unit radius, if you like. And then at time t, the membrane is displaced from the mean position, and let the vertical displacement at the point xy be z of x comma y comma t. Then what is the governing equation for this vibrating membrane? The governing equation can be derived. It is c squared times del 2 z by del x squared plus del 2 z by del y squared equal to del 2 z by del t squared, equation 5.1 in the displayed slide. Now, to derive this equation, you have to use certain basic physical principles, some conservation laws, and that derivation can be found in the book by Kreyszig's Advanced Engineering Mathematics, 8th edition, and c is the wave speed. Okay, so now we have got this partial differential equation 5.1. Let us look at a special solution of the form z equal to a cos pt plus b sin pt into u of x comma y. Let us look for standing wave solutions, as they would call in physics. So we should substitute 5.2 into 5.1. What do you get? Substituting 5.2 into 5.1 will immediately give you the next displayed equation, c squared a cos pt plus b sin pt Laplacian of u equal to minus p squared into a cos pt plus b sin pt into u. Now, you might ask, 5.2 is a rather specialized solution. Well, once we find various solutions like 5.2, we can always resort to taking superpositions of these specialized solutions and obtain more and more general solutions. And we shall see that this project can really be taken to completion. So, let us look at this last displayed equation in the slide. A cos pt plus B sin pt can be cancelled out, and we get the equation c squared Laplacian of u plus p squared u equal to 0, or p squared by c squared has been called k squared, and we get the partial differential equation Laplacian of u plus k squared u equal to 0. This equation is called the Helmholtz's equation or the reduced wave equation. So, now how do we deal with this Helmholtz's equation or reduced wave equation? Remember that our membrane is circular. The membrane is the disk x squared plus y squared less than or equal to 1. So, we must now resort to polar coordinates. We must put x equal to r cos theta, y equal to r sin theta. And it is an interesting exercise to write the Laplacian in polar coordinates. What happens when you write the Laplacian in polar coordinates? You get the last displayed equation in the slide. Again, I must remind you that we are working in 2 dimensions. The membrane is 2-dimensional. You could also look at what happens to the Laplace's equation in 3 dimensions. X equal to r cos theta sin phi, y equal to r sin theta sin phi, z equal to r cos phi. The Laplacian in 3 dimensions takes a rather ugly appearance, and the calculation is going to be horrendous unless you use a little bit of cleverness in deriving it. Let us leave the 3-dimensional case aside and let us come to the 2-dimensional case. As explained, the Helmholtz's equation becomes del 2u by del r squared plus 1 upon r del u by del r plus 1 upon r squared del 2u by del theta squared plus k squared u equal to 0. Now, we must separate variables. We must separate the radial and angular variables and look for solutions of the form u of r theta equal to Vr cos n theta. Now, the n must be an integer. Why? Because remember that the solution is periodic with period 2 pi. U takes the same value when theta takes the value 0 or when theta takes the value 2 pi, 4 pi, 6 pi, etc. U takes the same value at all these points. So, this n which appears in the factor of cos n theta must be an integer. Okay, so now you substitute u of r theta equal to Vr into cos n theta into the last displayed equation in the slide, del 2u by del r squared plus 1 upon r del u by del r plus 1 upon r squared del 2u by del theta squared plus k squared u equal to 0. Separate the variables, and the V equation assumes a very interesting form, namely r squared v double prime plus r v prime plus k squared r squared minus n squared v equal to 0. As you see displayed on the slide, this equation is the Bessel's differential equation after a little bit of rescaling. This is basically the Bessel's equation. So, what is the indicial equation for the Bessel's equation? It is rho squared minus n squared, and only the positive index will give you a solution which is relevant. Because the equation, the Bessel's equation, has solutions x to the power rho times a power series, x to the power minus rho times a power series, where rho squared equal to n squared or rho equal to plus minus n. Since both rho and minus rho appear, we can assume rho is positive. So, it is going to be x to the power n times a power series, x to the power minus n times a power series. But we have to discard the rho equal to minus n, because what is happening to the center point of the vibrating membrane? It is vibrating and the displacement is finite. If rho equal to minus n, then at r equal to 0, the solution will become r to the power minus n, and that becomes infinite when r equal to 0, and that is physically not tenable. So, because of the physical consideration of finite displacement of the origin, we must keep only that root rho equal to n, and the solution is the Bessel's function of the first kind, Jn of kr. So, the solution V of r is Jn of kr. So, finally, we have the solution z of x comma y comma t equal to Jn kr into a cos ct plus b sin ckt cos n theta. Since the membrane is clamped along the rim, we see that the solution must be 0 when r equal to 1 along the rim of the percussion instrument, that the rim doesn't undergo any displacement, it is always fixed. So, the function must vanish when r equal to 1. So, when r equal to 1, which term must vanish? It is a Jn term, namely Jn of k must be 0. So, the frequency k must be a 0 of the Bessel's function Jnx, and so there are infinitely many such values of k, because the Bessel's function Jnx has infinitely many zeros. So, the frequencies form a discrete set of values, and the most general solutions are then obtained by superpositions with coefficients that are determined via certain initial conditions and Fourier analysis. Again, we shall illustrate this through a simple example where the oscillations are assumed to be radial. Oscillations are assumed to be radial means that n is being taken to be 0. So, the cos n theta term disappears. That is, for the radial oscillation there is no dependence on the angular variable, and so since n is 0, Jn kr simply becomes J0 of kr. We are looking at Bessel's equation of order 0, and so our solution now assumes the form J0 kr into a cos ckt plus b sin ckt, and the k runs through the discrete set of zeros of J0x. Let these zeros be denoted by zeta 1, zeta 2, zeta 3, etc. Then the most general solution will be a superposition of these, namely z of r comma t equals summation j from 1 to infinity J0 of zeta j of r into a j cos c zeta jt plus bj sin c zeta jt. Now, the zeros of the Bessel's function are available in tables, they are available through Mathematica, they are available all over the place. So, we do not have to worry about what are the exact values of these zeros, zeta j's, they are available. Put t equal to 0 and we get z of r comma 0, which will be summation j from 1 to infinity aj j0 zeta j r. But this is known, the initial displacement is known to us, it is going to be f of xy. Similarly, differentiate this last equation for z with respect to t and put t equal to 0. Then the bj's will survive, the aj's will go away because the cos becomes a sine and the sine becomes a cos. And so, we have the following pair of equations determining the coefficients aj and bj. So, which are these two equations? Z of r comma 0 is summation j from 1 to infinity aj j0 zeta jr, zt of r comma 0 is summation j from 1 to infinity cj j0 zeta jr, where cj denotes j bj zeta j little c. All those constants have been lumped into one constant, capital Cj. In order to proceed further, we need a result from analysis called the Bessel expansion theorem, and we are not equipped to prove the Bessel expansion theorem. The result is available in this literature that I have cited, G. N. Watson, Treatise on the Theory of Bessel's Functions, 2nd edition, Cambridge University Press, 1958. So, the Bessel expansion theorem is available in this Treatise on Bessel's Function, and we can use this Bessel expansion theorem and we can determine AJ's and CJ's. So, let us now state the Bessel expansion theorem. Theorem 48. Suppose f of r is a smooth function on the closed interval 0, 1, then it admits a Bessel expansion f of r equal to summation j from 1 to infinity aj j0 zeta jr, where the coefficients aj are uniquely determined by the following formula, which is due to Lomel. Aj equal to 2 upon j1 zeta j squared integral 0 to 1 r f of r j0 zeta jr dr, where j1 is a Bessel's function of order 1. J0 prime is minus J1, that is how this comes. So, the coefficients Aj and Bj appearing in the solution of the vibration problem can be recovered from Lomel's formula applied to the initial conditions Z of r comma 0 and Zt of r comma 0. Good. So, now there are some exercises on Bessel's functions and write the Bessel's ODE in self-adjoint form. Namely, that is a form in which the Bessel's function appears. You divide by x and you get xy double prime plus y prime plus x minus p squared xy equal to 0. The first two terms xy double prime and y prime combine as d dx of xy prime. This form is called the self-adjoint form of the Bessel's function. Now, let us take a 0 of the Bessel's function and let us see the orthogonality properties of zeros of the Bessel's function. So, if you take phi u of x equal to jp xu, then I can get the expression x d dx whole squared phi u of x plus x squared minus u squared minus p squared phi u of x equal to 0. Using this expression, you must prove the orthogonality properties of the Bessel's function, namely jp of zeta x, where j varies from 1, 2, 3 up to n, is an orthogonal system over the interval 0, 1 with weight function x. So, this is the orthogonality property of Bessel's function. So, you see what we have seen is that the vibration problem has led us naturally to an orthogonal family of functions on the closed interval 0, 1 with a certain weighting function x. This is how the orthogonal functions appear naturally in physics and analysis. Here are some more exercises on the zeros of Bessel's functions. So, some of these formulas are due to Lommel, and a very interesting treatise is the theory of sound by Lord Rayleigh. So, the orthogonality property of Bessel's function has been established through physical considerations by Lord Rayleigh in his monumental treatise Theory of Sound volume 1 and volume 2, which appeared in 1945. Even to this day, it is a very beautiful book, it is very relevant. There are numerous experiments with vibrational problems that has been described in great detail. It is also mathematically very rich. So, now you might ask one question, okay, we have obtained a solution to the Cauchy problem, c squared Laplacian of z minus del 2z by del t squared equal to 0 with initial conditions f and g. How do we know that the solution that we have obtained is unique? The Bessel expansion theorem and Lommel's formula gave us one particular solution. Maybe there are other solutions. So, how do you know that the formula that we have obtained is the only solution? So, now we turn to the uniqueness features of the solution of the Cauchy problem. Suppose we have got two solutions of the wave equation with the same Cauchy data, same initial velocity and same initial displacement, and let these solutions be z1 and z2. Then, since the wave equation is a linear differential equation, z1 minus z2 is also a solution of the wave equation. Call z1 minus z2 as capital Z. So, capital Z also satisfies the wave equation with 0 initial data, namely c squared Laplacian capital Z minus del 2 capital Z by del t squared equal to 0. Capital Z at time t equal to 0 is 0 and capital ZT at time t equal to 0 is 0, and the value of capital Z along the rim of the membrane or along the edge of the membrane is 0. So, how do you know that this capital Z is 0? If we prove that this capital Z is 0, then little z1 equal to little z2 and our uniqueness theorem would have been established. So, let us prove that if we have the 0 Cauchy data, then the solution is compulsorily 0. So, to do that, the idea of the proof that we employ is called the energy method. Use the principle of conservation of energy for the wave operator. So, multiply the differential equation by z sub t. So, we get c squared zt Laplacian of z minus zt ztt equal to 0. Integrate with respect to the space variables exactly as we did for the one dimensional wave equation. Remember, we multiplied by ut and integrated with respect to the spatial variables x and y over the disk. So, we get d dt of double integral zt squared dx dy over the disk d plus integrate by parts zt zxx throw one of the x derivative on the zt term. When you integrate by parts, the boundary terms will cancel out, they will become 0 because of the 0 initial data and the 0 boundary data. So, we get c squared double integral over d capital Z xt capital Z x plus capital Z yt capital Z y dx dy equal to 0. From this we infer that the energy Et, which is the double integral c squared zx squared plus c squared zy squared plus zt squared dx dy equal to 0. The energy is conserved. Constancy of energy or the law of conservation of energy. Put t equal to 0, since the zt was 0 initially and z was identically 0 initially. So, z is identically 0 initially. So, zx is 0 initially, zy is 0 initially. So, this Et is identically 0 and therefore, c squared zx squared plus c squared zy squared plus zt squared must be 0. So, all partial derivatives of z must be 0 or z must be constant, and this constant must obviously be 0 because the membrane is clamped at the origin, and so along the rim z is 0. So, z must be 0 throughout since it is constant. So, we have proved that the solution that we obtained is the only solution. Here are a couple of exercises for you. Use this energy method to show that if we solve the heat equation ut equal to Laplacian of u of xy 0 equal to f of xy, the initial distribution of heat is f of xy and the value of u along the boundary is identically 0. So, the boundary is permanently kept at 0 temperature. Then the heat distribution is unique. The solution of the heat equation with these initial conditions is unique. Again, you should multiply the differential equation by u and you should integrate with respect to the space variables, and you will realize that the heat distribution is monotone decreasing. Please try these exercises and we shall continue. So, for more detailed discussion on wave phenomenon, I refer you to Courant and Hilbert, Methods of Mathematical Physics, Volume 1. We already cited this reference many times before. The discussion of the circular plate, not a circular membrane, is on page number 307, 308. This will involve Bessel's functions of imaginary order, I rho, also known as the modified Bessel's functions. You will see the biharmonic equation coming up. And then I already mentioned Lord Rayleigh's theory of sound, Volume 1, Volume 2. And there are also applications of Bessel's functions to skin effect. When you see electrical current passing through a long cylindrical coaxial wire, the outer layers of the wires get heated up and not the inner layers. This is called skin effect. So, for that I refer you to the small book by Frank Baumann, Introduction to the Bessel's function. The Bessel's function appear in optics. The radii or the successive interference fringes due to diffraction from a circular aperture are given in terms of the zeros of the Bessel's function. And of course, the monumental treatise of G. N. Watson that I mentioned earlier. There is also a small book by Byerly which is particularly recommended for the historical sketch that he offers at the end of the book, and this book is available online. So, these are number of references for wave phenomenon and for Bessel's functions that you may consult with profit.